Hello everybody, welcome to my presentation. I'm Elham Ahmadi. I'm a PhD student at Federal University of Santa Catarina. In this presentation, I'm going to talk about near-optimal coordination of vehicles at an intersection plaza using finite Fourier series. The first objective of this paper is proposing a new model for vehicle coordination at intersections to break line-lasting paradigm of road use to maximize the traffic efficiency and also to better use of the available intersection infrastructure. And the second objective is generating optimal trajectories of vehicles without predefined paths to minimize some criteria such as travel time or fuel consumption and considering traffic safety as a main concept. Before discussing problem formulation, here I introduce the concept of plaza. Basically, plaza is a free space in which vehicle can move anywhere without being bound to any specific path or movement. As an example, in this figure, the yellow area shows a plaza which can have various layouts such as intersection, roundabout, and so on. T1 and T2 shows the trajectories of two vehicles that are free to move inside the plaza, and these two figures shows vertical and horizontal coordination of these two vehicles. In this figure, the green line shows the distance between these two vehicles and ds is minimum safe distance. The idea here is to keep safe distance between vehicles in inner direction to avoid collisions. Here we use a four-leg intersection to introduce our concept. A plaza can be modeled by four intersection boundaries shown by black dashed line in this figure named IB1 to IB4. Each intersection boundary can be modeled by a well-defined exponential function as follows, in which fa shown by this formulation, in which r0 to r3 are intersection parameters. First, we use a simple equation of motion that modeled as a particle by this equation. Here, ax and ay are the acceleration of each vehicle in coordinate x and y, and here k is the number of vehicles at intersection plaza. The total absolute acceleration can be calculated by this equation, and the total speed increment delta v is a summation of each delta vj, which can be computed by a numerical integration of each aj. And here t is a completion time, is the time taken by vehicle to cross the intersection plaza. And next we have the problem constraints, consist of vehicle's physical constraint, vehicle-to-vehicle collision avoidance constraint, and plaza boundaries constraints. Finally, the ITOP can be shown by this formulation, which is about minimizing an objective function subject to several types of constraints which discussed here. The states are position and speed of each vehicle, and the control variables are completion time t and acceleration of each vehicle. We propose to using finite Fourier series to solve the ITOP. The idea here is that by using Fourier approximation, we can approximate any periodic function. As you can see in this figure, the blue curve shows Fourier approximation of red curve with respect to the different number of Fourier terms, or n. So, the position state variables can be approximated by this equation, in which n is the number of Fourier terms, b0, bn, and cn are Fourier coefficients that should be determined. Here, tau is a scale time which is between 0 and 1. Then this representation of state variables are imposed to the dynamics, and we can evaluate the required acceleration. Finally, by using a finite Fourier series, the ITOP can be transcribed into this nonlinear programming problem in which the decision variables are completion time t and unknown Fourier coefficients. In this part, I'm going to discuss the numerical results. I consider three scenarios. In the first scenario, I consider three vehicles shown by colored squares in this figure, and ds is 1 meter. In this figure, we can see the generated trajectory by using finite Fourier series. As you can see, the trajectory generated by finite Fourier series deviated from what would be expected in a movement-based method, and also it is clear that the vehicles follow free trajectories. And in this figure, we can see the distance between every two vehicles which are above the minimum safe distance, and this shows that there is no collision between vehicles. In the second scenario, I selected a relatively large ds which is 7 meters. In the first scenario, there is no collision avoidance constraints in the model, and this figure shows the generated trajectories. And as you can see in this figure, the distance between vehicle 1 and 3 goes below the minimum safe distance, and this shows the trajectories collide to each other and there is a collision. In this scenario, we impose traffic safety constraints into the problem, and this figure shows the generated trajectories. And this figure shows that the traffic safety constraints are satisfied. In the last scenario, I consider a more complicated case with 8 vehicles shown by colored squares in this figure, and we can see the generated trajectories by using finite Fourier series. And this figure shows the distance between every 2 vehicles. We've shown that the traffic safety constraints are satisfied. And here is the conclusion. The proposed FFS method can generate feasible trajectories whose solution is near optimal. The computational time of FFS method depends on the number of discretization points, the number of Fourier terms, and the number of vehicles. And the generated trajectory by FFS can be used as an initial guess for other optimal control methods. Thank you for watching this video.